All right, so yesterday we talked about substitution reactions, and we said a substitution reaction, at least a nucleophilic one, is where your nucleophile replaces some sort of leaving group on an organic molecule. And we said it can go through a two-step process where you have a carbocation intermediate, or it can go through a one-step process. We said the main difference between these are the rate equations, right? So experimentally, the rate for the one-step reaction is going to be second order, meaning changing the concentration of either reagent will affect the rate. Where with the two-step reaction, the rate is first order, and the only thing that affects the rate is the concentration of your organic substrate with the leaving group on it. All right, so today what we're going to do is investigate this in a lot more detail. We're going to look at the role of the electrophile. I'm going to start with the SN1 reaction. And what I want us to do in this one is consider the starting material, and I'm going to abbreviate that as SM, with the leaving group attached. And I'm going to give us two options. Option A up here versus option B. We're going to have two competing reactions. So in reaction 1, I have a leaving group and I have a nucleophile. And I'm just going to draw it with a negative charge. And in option 2, the reaction looks remarkably similar, but the starting material is slightly different. So the thing we're really going to be comparing here are these two starting materials with the leaving group. All right, so in an SN1 reaction, what's the first step going to be? Who remembers? Is the nucleophile going to attack and kick off the leaving group all in one step, or is this going to be a two-step? Two-step. So what's the first step going to involve? The leaving group falling off. So in either of these, the leaving group could fall off. Oops. So in this case, we would have a positive charge plus our nucleophile over here, plus my leaving group that fell off with a negative charge. Down here, things will look pretty similar. And then the next step, what happens in this next step? Yeah, the nucleophilic attack, right? The nucleophile will add to the carbocation. Let me slide this over a bit. All right, so we've got two competing reactions that we're considering here, reaction A versus reaction B. All right, I want you to check with your neighbor, and I want you to determine which of these reactions is more likely to proceed given the arrow pushing that we've shown. So check with your neighbor and see if you can argue, hey, I think reaction A is going to be favorable, or hey, I think reaction B is going to be more favorable, and talk about why. All right, I'm going to stop you really quick. What's the rate limiting step for an SN1 reaction? Is it the first step or second step? The first step. So really what we're doing in either of these reactions is we're comparing the first step and kind of ignoring the second step. So we're comparing the things that I've highlighted in the boxes, right? So really the only difference is what? So in both cases, the leaving group falls off, right? What about the products when we look at these? What's really the main difference? Yeah, if we look at this carbocation right here, is it primary, secondary, or tertiary? Primary. Okay, so underneath here, I'm just going to say this is a primary carbocation. What about underneath here? What is this one? Tertiary. Which one is more likely to form, and why? Tertiary, why? Because it's more stable, right? Okay, so down here we can say reaction B is more favorable / likely because it gives the more stable carbocation. In addition, it has the lowest activation energy. If we think about ripping off that leaving group is going to be easier if the transition state is highly stabilized with hyperconjugation. So it's kind of along the same lines. All right, so this gives us a pretty good insight. What's the most stable carbocation we can possibly have? Is it primary, secondary, tertiary, methyl, resonance? What's the best? Resonance. Okay, so up here we can say resonance is the best, followed by tertiary, followed by secondary, followed by primary, followed by methyl. Okay, so over here we could say it gets more stable carbocation, the more we either have resonance or highly substituted cations. All right. This also correlates to the probability of SN1 occurring. So increasing probability of SN1. This is really important when we think about this, right? Because in SN1 reactions, formation of the carbocation is the rate limiting step. Therefore, we always need to ask ourselves, what's the likelihood of making that carbocation? It's going to be a lot more likely if it's a stable carbocation, right? Make sense? All right, let's go on to an SN2 reaction. And again, we're going to consider the reagent with the leaving group, just like we did in the prior one. All right, so again, we're going to do the same reactions. Leaving group with a nucleophile for A, and then B will kind of do something similar. Let's consider the arrow pushing for this reaction. What's involved in the arrow pushing? Is it one step, two step? How many arrows do we need? See if you can add in the arrows on your own for an SN2 reaction. So in an SN2 reaction, does your leaving group fall off first? No, what happens to it instead? Nucleophilic attack. The way I like to imagine this is your nucleophile is hitting that carbon and shoving off your leaving group all at the same time, right? So in this case, your nucleophile is going to attack in and kick off your leaving group all in one go. So it's not going to be a two-step process. Instead, it's just going to be a direct one-step process. All right, we can do the same thing down here. We can say, all right, it could attack this carbon, kick off our leaving group. All right, so just like before, I want you to ask yourself and then check with the neighbor, which of these is more likely to occur via an SN2 process, A or B? I feel like every year people look at this one and they're like, well, up here it was this answer, so it's probably flip-flopped for that one. But still, like I said, anytime we're looking at something, focus on the why. Why does this happen? Why is this favored? All right, so let me maybe give you a few pointers. The leaving group falls off in either case. Is it very different between reaction A and reaction B? Nope, the leaving group falling off is the same for reaction A and reaction B. What's the only difference then? It's the nucleophile going in. All right, so if you're a nucleophile and you need to hit that carbon that has a leaving group on it, which carbon is going to be easier to hit? The carbon in A, meaning this carbon that's highlighted right here, or will it be easier to run into this carbon down here in B? A, why? It's easier to get to, right? It's not as blocked by all these methyl groups kind of hanging out in space. So when we look at this one, the way we describe this is all of these groups kind of crowd things. This is called steric hindrance. So the nucleophile is going to have a much, much harder time reaching that carbon than it will in example A, right? So in this case, we're not really looking at carbocations. Instead, we're looking at how crowded things are. So if we look at carbons, we can have a tertiary carbon with the leaving group. We can have a secondary carbon with the leaving group. We can have a primary carbon with the leaving group. Or we can have a methyl group with a leaving group. All right, we know that methyl groups are far and away the smallest, meaning these are less bulky. And again, this corresponds to the likelihood of an SN2 reaction. So here's when things start to kind of gel. All right, what if I have a tertiary carbon with the leaving group? Do you think it's more likely to be SN1 or SN2? SN1, we said tertiary carbons give us relatively stable carbocations, so it would likely proceed through an SN1 reaction. For down here, we said a tertiary carbon's super crowded, so it's very unlikely to do SN2. All right, what about a primary carbon? What do we do, SN1 or SN2 normally? Yeah, SN2. Primary carbons aren't very crowded, which allows for SN2 to occur, but at the same time, they don't give very stable carbocations, so it's very unlikely to do SN1. The tricky thing is, well, what about secondary carbocations? They're kind of in the middle, right? Not super happy, not super unhappy. Are they hindered? Yeah, kind of not. With secondary carbons, things get a lot trickier, but for right now, we're going to focus on the extreme cases. Yeah?
Why the secondary don't do rearrange to be the...
Yeah, so that's a good question. So Jade was asking, if we have a secondary carbocation, can it rearrange? Absolutely. So we're going to talk about rearrangements a little later, but for right now, I just wanted to get through the general idea of why things are more likely to be SN1 reactions when they're highly substituted, but way less likely to do SN2 reactions when they're highly substituted. So we've got these competing trends going on. Yep. Yeah, I think I'm recording it. Yeah. All right, so let's go to the next one. Next one is stereochemistry. So let's, again, start with SN1 reactions. And I'm going to give you a molecule. Looks like this. All right. In an SN1 reaction, whoops, I don't want a zero there. In an SN1 reaction, what's the very first step going to be? Is the chloride going to attack the carbon and kick off the iodine all in one step? Or is the iodine going to fall off first? Iodine will fall off first. Okay? So first step, we know that iodine will fall off. When we do this, what's going to happen is something kind of unique. So this carbon that was attached, I'm actually going to draw out like this, has changed during this process. We know that it is a carbocation, obviously, but let's think about the hybridization. In the beginning, what was the hybridization? It was sp3. What about the hybridization over here now? sp2. So we've changed the hybridization of the carbon once the leaving group's fallen off. What else is unique about an sp2 carbon? What orbital is very, very important? The p orbital. Okay, so in this sp2 carbon, we've got this p orbital kind of hanging up and down, so it can go both in and out of the plane, right? All right, so now we've got chloride floating around. That's going to be our nucleophile in this case. We know it needs to attack that carbon. Do you think it's going to attack from the top or from the bottom? This is interesting, right? So the iodine fell off. It's kind of fell off underneath it. So the chloride in this case, main question is, will it attack here or will it attack there? Do you think it'll attack both? What do you think? What's the geometry for this intermediate? It's trigonal planar, right? So if it's trigonal planar and it has a p orbital going up and down through it, and you're the chloride kind of floating off in space, you can kind of pick top lobe or bottom lobe. Doesn't really matter in this case. All right, so let's consider the top lobe attack. If that's the case, the chlorine would be attached at the top. If we did the bottom lobe attack, it would look a little bit different. It would look like that, right? So we might get two different products out of this reaction. My question for you is, what's the relationship between these two products? They're enantiomers. Why? Let's go up here. We've got a stereocenter. Is this R or S? It's a little bit tricky. Be S for that stereocenter. Down here we have another stereocenter. Would this be R or S? Be R. So you see how we flipped our one stereocenter? These are also mirror images of one another, but non-superimposable. So these would be enantiomers. All right, so now getting into the really nitty-gritty one. Do you think the topside attack is going to occur at equal probability as the bottom side attack? Give you a hint. Iodine is kind of hanging out as this big ionic sphere right there. Do you think it's going to be easy for that chloride to pass that iodine? No, so in this case, what happens here is a proximity effect. So it's a little less likely to attack this face where the leaving group fell off. The leaving group is almost acting as like a blocking group. It's hanging out in space on that side. It's making it harder for that chloride anion to find its way to that p orbital lobe. So it's a little less likely. So let's make a note. The note is that SN1 reactions give mixtures of stereoisomers. In the above example, we got enantiomers, but in other examples, we might get diastereomers. It's always good to check. With a slight preference for inversion. So now the question is, what the heck do I mean by inversion? What that means is that the nucleophile slightly prefers to be on the opposite side of the leaving group. So you see how over here, this iodine was kind of on the bottom face, but the preferred side for the nucleophile to attack on is the opposite face. So really it's supporting the idea that once that leaving group falls off, it kind of weakly blocks the ability for the nucleophile to attack that exact same side. Does that make sense? But in either case, we will get a mixture. All right, now let's take a look at SN2. All right, SN2 is a little bit trickier. All right, with SN2, I'm going to give us an example molecule. And I've got my nucleophile. In an SN2 reaction, we can have a situation where the nucleophile attacks the same side as our leaving group. So it's kind of attacking the face of the carbon where the bromine's attached, and then the bromine can get kicked off. All right, so let's consider the transition state for this. Oops, should be a straight line. So during this transition state, we're going to be forming a new bond to our nucleophile. At the same time, our leaving group is falling off. So make sure you put these in brackets and do the double dagger to indicate this is the transition state. All right, we're missing something though in our transition state. What am I missing? Charges, right? So is the nucleophile going to be a full negative? Will it be neutral, or will it be somewhere in between in the transition state? In between? Okay, so I'll go ahead and say this nucleophile is partial negative. What about the bromine? Be partial negative as well because it's halfway off. And then we could say, all right, during this process, we can infer that really the other groups are staying put. They're all going to be on that left-hand side. But then in our final process, our nucleophile would be attached here. And then our bromine would be kicked off as our leaving group. Make sense? So this is a reasonable theory. All right, let's do option 2 though. All right, option number 2, we're going to do the same thing. But how else could the nucleophile attack that carbon? What do you think? The other side, right? So instead of attacking the front side, maybe we attack the back side. So it swings around, attacks the back side, and then kicks off that leaving group. Let's consider this transition state. All right, in this transition state, the nucleophile is going to be forming a bond to this carbon. Hydrogen's going to kind of be sticking up like this. Methyl group's going to be like that. Ethyl group's going to be sticking down. And then bromine will be off here. And just like before, the nucleophile will be partial negative. The bromine will be partial negative. And then quickly we can say, all right, that means that once all is said and done, the nucleophile will be attached on the opposite side. All right, so between option 1 and option 2, these both would be a second order reaction, right? Both seem to follow reasonable arrow pushing. My question for you is, which one do you think is more likely and why? Check with your neighbor and see if you can explain it to your neighbor.
Well, because the first one, if you push Yeah, like the bromine is kind of blocking the nickel to get from the walls. If you could think of that,
All right, does anybody want to share a theory? What do you think, Awesome? Okay, so Awesome is saying basically it might be too crowded to do the front face attack. I think that's a reasonable theory. Does anybody have another theory? What do you think? I think you're hitting the nail on the head. So it's going to be hard for people on the internet to hear that, so I'll try to condense it down. So instead of talking about it being crowded, you're saying maybe being crowded doesn't matter. Maybe it's more about the charge, right? And I agree with that. If we look at this one, we've got these two things with partial negative charges being forced into close proximity to one another, right? Where on option 2, the things with partial charges in space are separated really far apart in space from one another. Which one's going to be happier? The bottom one's going to be a heck of a lot more happier. So we can go ahead and we can say, really, this is a bad interaction. It's destabilizing. And not likely to occur. So even though we came up with this theory, we can quickly say this is a really unlikely thing that will occur because we know that the transition state would force those electron clouds into really close space to one another. Therefore, we're probably not going to observe this product. Option 2, on the other hand, seems perfectly reasonable. Does anybody remember the shape of this sort of molecule? So we've got 5 different groups on it, on that carbon. Yep, trigonal bipyramidal. I know, you're like, that was Gen Chem, and you told me I didn't have to remember that. All right, so the cool thing with this is you see how if we're comparing our starting material on the left-hand side to our final product, the nucleophile is actually attached to the opposite face, right? So in this case, we call that an inversion. Does that make sense? So it's kind of like an umbrella flipping inside out almost. So the nucleophile hits the backside, your umbrella kind of goes flat, and then it inverts all the way. So it's like an umbrella on a windy day is a way of thinking about it. All right, so let's make a note here, kind of like we did previously. The note is that SN2 reactions do not give mixtures. You only get one product that is inverted. Does that make sense? So SN2 reactions, we said we get a mixture of stereoisomers. That's a big clue. If you only get one product, it's a big clue that you only get, or that you're going through an SN2 pathway. So more experimental evidence that we can use. All right, I know this is a lot of things to pay attention to, but we'll try to go through slowly and address the why for each of these rather than just trying to brute force memorize everything. All right, we've got about 10 more minutes, so let's continue on and talk about some other variables to consider. So right now we've been really focusing on the organic substrate with the leaving group, right? Or the electrophile. However, we haven't really talked about the nucleophile too much. So let's again start with the SN1 reaction. Let's do A up here. We'll do leaving group plus iodide as our nucleophile versus the same starting material, but let's do bromide as our nucleophile here. What's the first step going to be for an SN1 reaction for either of these, A or B? Leaving group falling off. All right, so in either of these cases, our leaving group could fall off. Why are these good candidates for SN1 reactions and not SN2 reactions? Yeah, because they're tertiary carbocations, which means it's way, way, way more likely that these will do SN1 than SN2. All right, and then next step, what would occur for our next arrow pushing? Yeah, nucleophilic attack. So we could have iodide attack in or bromide attack in, depending on which reaction we're looking at. All right, my question for you is which of these reaction pathways is going to be faster or more likely? Check with your neighbor and see. All right, let's do a super quick survey. Raise your hand if you think A will be faster. Raise your hand if you think B will be faster. Raise your hand if you think it'll be a tie. Ah, this is tricky. All right, so let's look at A. What's the rate limiting step in A? First step or second step? Let's highlight it. So in reaction A, what's the rate limiting step? Is it the leaving group falling off and giving you the carbocation? Or is it the nucleophile attacking your carbocation? It's a leaving group falling off. That's something that we went over yesterday. We said that this area highlighted in yellow is going to be the rate limiting step for that reaction, right? So it's going to be the thing that ultimately determines how fast this reaction goes. All right, and then underneath here, same story. Got this one. That's going to be our rate limiting step for the second one. So in either situation, the rate limiting step is the leaving group falling off. Does the nucleophile do anything in the rate limiting step? Does it? I don't think so. It's just kind of floating around as an anion. All right, so let's make some notes. So the note is the nucleophile does not participate in the rate limiting step. Therefore, we can really ignore it in this situation, right? Because it's just not doing anything. All right, so if we ignore our nucleophiles, so in the top one, we'll ignore iodide, so I minus, and in the bottom one, we'll ignore Br minus. Is there really a difference between A and B? No, not at all. So the nucleophile does not participate in the rate limiting step. The rate limiting step only involves the leaving group falling off. All right, so with that one in mind, which one's going to be more likely? Or do you think it's equally likely? I'd say equally likely, right? Because the nucleophile really doesn't do anything, and other than the nucleophile, it looks 100% identical between reaction A and reaction B. So which reaction is faster and more likely? They are equally likely. All right, so let's make a note on this. The note is an important one. The nucleophile doesn't really matter for SN1 reactions. Since it isn't involved in the rate limiting step. So that was kind of a trick question for you. But it's an important thing to do. Like I said, don't just always take what the textbook says at face value. Sometimes you have to stop and really dig into the why and challenge yourself. Yep.
So for the second step, the non-rate limiting step, since bromine is smaller, wouldn't it like fit into the central carbon more easily? And since it's smaller, does it also have more kinetic energy?
Yeah.
Would it be moving faster? Is it more likely to hit?
So Kristen was asking, all right, so we know that the first step's rate limiting, but what about the second step? And you're saying bromide is smaller than iodide, so couldn't it reach into that pocket and do that next attack more readily? We're going to address that next. But the reality is with SN1 reactions, that's just not a rate limiting step, so it doesn't really impact the kinetics of the reaction at all, so we don't really care about it too much. That's a great question, though. All right. So let's go to an SN2 reaction, and that will actually get back to your point. So SN2, we have reaction A. And again, I'm going to keep the electrophiles the same. Then I'll do reaction B down here. Same electrophiles, but in this case, I'm going to change my nucleophile. And in both of these, just like we saw before, we're going to do that backside attack, kick off our leaving group, all in one step. And Lg minus. All right, so I think this is getting back to Kristen's point, where it's like, what if the nucleophile does matter, though? So in this case, the nucleophile attacking is involved in the rate limiting step. Which nucleophile do you think is going to be more aggressive with its attack? I'll give you a hint. Okay, if something's less stable, it's going to be more aggressive. Which one's going to be less stable with a negative charge? Br minus or I minus? Less stable. Let's go back to our cardio rules, where we looked at stability of anions. So for charge, they're both -1, tie. Then we go to atom, right? So iodine versus bromine, are they in the same column or same row? Same column, right? So which one's going to be more stable, the larger atom or the smaller atom? Larger. Okay, so in this case, which one's larger? So this is larger equals more stable. This one will be smaller and less stable. All right, so in this case, Br minus is more nucleophilic because it is less stable. put an important note here. We are ignoring solvent. And that note's kind of an important one, because what happens when an anion is put into a solvent? What does that solvent typically do to the anion? So what happens if you put like a sodium cation into water? What happens to that sodium cation? Water will essentially form a shell around it. How many of you remember that from Gen Chem? Like a sphere of hydration. In this case, we're kind of ignoring the solvent effects for right now, but solvent also plays a key role that we'll talk about later. But for right now, we're just going to kind of ignore solvent and assume that it doesn't play a major role for these SN2 reactions. All right, so that's where we're going to stop today. Tomorrow, what we're going to do is we're going to talk a bit more about nucleophiles and then get into some more complicated examples.